Now, the last topic for this chapter on solutions and mixtures of different types, the last topic is called colligative properties. Now, what this basically colligative properties mean are properties that depend only on the number, not the type of particles present. It doesn't really matter what it is, just how many of them we have will determine this property. And the two properties I'm talking about here have to do with freezing point and boiling point changes, as I'll explain. So it depends on the number of particles, not their identity, not what they are. It makes no difference. Let me explain. You see, if I add a solute to a solvent, if I add salt to water or sugar or something to water that dissolves, it's going to change the boiling point and it's going to change the freezing point. I bet if you think for a minute, you could tell me how it's going to change the freezing point. What's it going to do to the freezing point of water when I add salt to it? Raise it or lower it?
Raise it.
Raise it. Lower it.
Sure. Raise it. Lower. Raise it.
Why do we put salt on roads? To melt. They always say it. To melt. To melt.
Sure.
Okay. Let's assume that that's not correct.
It is.
Okay. What would we want the water not to do on the roads?
Freeze.
I don't want it to freeze, right?
Yes.
So adding salt to the water that's on the roads would raise or lower the freezing point such that it would not freeze. It would lower. It's exactly right. That's one of the reasons you do it. And if I add, you ever notice your parents sometimes adding salt to water before they're going to boil the water? All right. I know most of you think it's probably, and it probably is. Most of your parents think, most of your grandparents probably think that's so you can flavor the water, flavor the spaghetti, whatever you're cooking. That's true. But what else does that salt do?
It makes it boil faster.
Both of those answers are wrong. Makes it boil, lowers the boiling point and makes it boil faster. All right, neither of those things are correct. It does not lower the boiling point. It raises it. It raises the boiling point, which would not make it boil faster, but rather make it harder for it to boil. Okay, so it's going to boil at a higher temperature. All right, let me show you. Basically, think of it this way. Remember this graph? I don't know if I hit the right button or not. Nope, I knew it. Remember this graph? Don't have to copy this. Just watch. Remember this graph? Remember that? This was the solid, liquid, and vapor phase, remember? And this is what? Melting point and boiling point. So if we're talking about water in this room at this pressure around sea level, the melting point of water is 0. And what's the boiling point of water? 100. Now, I want you to think of adding a solute actually makes it a lot harder for this stuff to freeze and a lot harder for it to boil. All right? It extends the liquid phase. Think of it this way. The boiling point being lower, it'll look something like this. And melting point being lower. The boiling point being higher, it would look something like this. All right? So notice the actual area that is liquid is extended. I've extended the liquid phase of the substance by lowering the melting point and raising the boiling point. Okay. The reason that happens is with those other particles of salt, the sodium ions and those chloride ions in there, it's harder for the water molecules to form their crystals, so it lowers the melting point. And it raises the boiling point for a similar reason. At the surface, there's just fewer water molecules able to boil, all right, and so the vapor pressure has to get higher for it to be boiling. All right, you have to increase the temperature up higher. All right, so basically think of it this way. Adding a solute extends the liquid phase of the substance. And this has some practical applications for us, which I've already mentioned 2. All right, I've already mentioned 2 practical applications. One is, and we use more salt on our roads than we use on cooking, believe me. by a lot. All right, most of the salt we manufacture is used on roads to keep the water from freezing. Of course, below a certain temperature, it's not going to work anymore. I think that temperature's like 14 degrees. They were saying this winter was a bad winter, and so even if you have, of course, in Berwick we never salt the roads. We only cinder the intersections. I don't think I've ever seen them actually throw salt on a road. They plow 3 inches off the ground and they cinder the intersections. So that's about it, basically. So anyway, but that's what it does on a sidewalk or whatever. There's something else we could use that for in a second, which you might be interested in for the lab tomorrow. But before we get to that, let me say something else. Salt's actually really good at doing this, better than sugar would be. Why wouldn't I want to put sugar on there? Well, I get a lot of ants come like spring. Sugar on the roads. But besides that, I wouldn't want, sugar actually isn't as good as salt is, because it turns out, since it only depends on the number of particles, not the actual identity, sugar just dissolves into one thing. Whereas salt, I'll bet you guys know, we've written this equation before, don't write this down, salt is going to break up into sodium ions, aqueous, and chloride ions, aqueous. Okay? So I actually get 2 ions per, matter of fact, calcium chloride, which you can also use as a ice melter. Calcium chloride, how many ions are they going to get from calcium chloride when he breaks up? 3. I'll get 1 calcium and chloride ions, 2 of them. And by the way, please do not put Cl2 over there. That's chlorine gas, not chloride ions. All right, good enough? Now, so it turns out that the number of particles for an ionizing solute, a solute that breaks up like salt does, actually multiplies the effect. It multiplies the freezing or the boiling point effect. So if the solute associates with the multiple particles, you have to multiply the freezing point change or the boiling point change by that number of particles, because it doesn't really matter what those particles are, just how many of them there are. Okay? All right, let's talk about each one individually. First the freezing point and then the boiling point. And I'll do a couple of examples. Well, actually, I'll do a total of 3 examples. 1 for the first one and 2 for the second one. And I'll also try to point out some other practical uses for them. All right, let's start with the freezing point depression. Freezing point depression. That means how much it's lowering the freezing point, depressing the freezing point. Not like clinical depression like I am right now. Talking about freezing point depression, lowering the freezing point. Adding a salt, or a solute, I should say, salt being one of them, to a solvent like water will lower the freezing point. And there are some practical uses for that. One of them being salt on roads, keeping the ice from forming on roads. But antifreeze in your car is another example. If you have just plain water in your radiator and you wake up tomorrow morning when it's below freezing, that water is not circulating anywhere to cool that engine off. It's going to be frozen solid. You're going to have antifreeze in there too, which most of you do. I mean, not most of them, all of you do. We all have antifreeze in our car. Antifreeze is a mixture in water of different things, usually ethylene glycol or propylene glycol. Is added to water, and so it will actually boil at a much higher temperature and it freezes at a much lower temperature, so that your car, when you wake up in the morning, it's below freezing, is not a frozen block of ice in your radiator. Okay. By the way, below a certain temperature, like if you live in Alaska or something, constantly very low temperatures, maybe even some of you have one. You have heaters for your car, because even antifreeze is only good down to a certain temperature, below which it'll freeze as well. But there's another good example, one that you'll be happy to know Anybody ever use, it says it right on here, anybody ever use rock salt for something besides just your roads? What'd you use it for? Yeah, ice cream. You scream. We all scream, actually, for ice cream. Ice cream, you scream. Anyway, this is the lab we're going to do. Guess what we're going to make?
Ice cream?
Yeah.
Yes.
You scream. We all scream.
Do we have to eat it?
Yeah. Yeah. If I set this up right, which I've done before, generally when I do this lab, I've done it in several different ways. I'm not sure what I'm going to do this year. I'm still not positive. I've tried it as individual, groups. Like last year we tried that. It's kind of messy, and it's kind of a pain. I've tried it making a large group of it. Anybody have an ice cream maker at home, like one of those big containers? Okay. I've tried it that way. As a matter of fact, if you guys can remember, both of you want to bring that in tomorrow. One of you want to bring one of those in. I might end up doing it that way. Either way, if we do it in a lab, we don't normally eat in a lab. As you all know, we never eat in a lab. So I generally have to take some precautions, and I will cover the tables up, and we'll have anything we're going to be mixing the stuff in is going to have to be actual stuff I buy from the store. You're not going to use beakers. You're not going to use spatulas. You're not going to use stirring rods. You're going to have to use like plastic spoons, sugar from the store, stuff like that. But either way, I'm working on it. We'll see what happens for that lab. If we do it one way or the other as a demo or as a full lab individually, we will do it tomorrow because you guys have the double tomorrow, right? We'll only need half of that period to review. The other half will be for that lab. Yeah, I told you this is the last topic for the chapter. The test will be on Wednesday. Tomorrow will be the review and possibly the lab, and then the test will be on Wednesday. All right, let's get into some calculations here. Ready? So if you do either way, you're going to have to do these calculations. There's the equation. I'll bet you could figure out what each of those things probably means. Delta TF. In your own words, what do you think delta TF probably stands for? What do you think the F stands for? Yeah, change in the freezing temperature. Right, change in the temperature at which something freezes, delta TF. The normal freezing point of water is what in Celsius? 0. So this will tell me how many degrees will it be higher or lower. If I add a solute, what's it going to be? Lower, right? Wow, this is tough. Lower. How many degrees lower? It will tell me by multiplying these two things together. Now, I bet you know what the M stands for because I told you on Friday that's the reason we covered that. Molality. Molality. Remember we did that Monday? On Friday? Remember? You don't remember doing molality. Well, you weren't here. Everyone else remember doing molality. Okay. You had to do some problems in the back of that worksheet as well, right? The one with the brackets. Okay. Now, the only thing left that you wouldn't know what it means, KF. Well, K, in chemistry, there are a lot of Ks. We generally use K to mean some constant, all right, because we spell phonetically in chemistry. K is for the constant, freezing constant. I'm not going to make you memorize these. You can write it down right here, but you will not have to memorize. KF equals 1.86 degrees Celsius per mole. Just write that down. That will be given to you on the test. You do not have to memorize it. 1.86 degrees Celsius per mole. Okay? By the way, they're also, both of them are up here. KB, we're going to get in a little bit. That's up here too. And both of those will be given to you on the test. All right, let's get to the first problem. We're going to do 3 of these. There's the first one. If I take some glucose and I add it to water, what will happen to the freezing point? And I'm telling you that glucose is a non-ion. I have to tell you that. It means it does not break up into ions. What you see is what you get. WYSIWYG. Ever hear that before? What you see is what you get. WYSIWYG. Now, remember, when I have equations of any size whatsoever, I usually have you write the given information down to the side and go from there. When I have stuff that's this short and this easy, I don't always make you do that. And this is a good example of where I wouldn't. Let's take a look at this equation. I only have 3 variables, one of which is a constant that I'm going to give to you anyway. So really I have two variables, one of which I'm solving for. So really I have one variable. It'd be kind of hard to mess this up, okay? However, this one variable that I do need, the molality, is not given to me, is it? So what should I do first? What do you think I have to do first, like I had to do on Friday? I got to calculate the molality. I'm given 30 grams of glucose in 600 grams of water, right? So molality is a lowercase m, not capital M, but lowercase m, equals moles of solute per kilograms of solvent. I always get somebody who wants to write times 100. Why do they want to write times 100? Because percents times 100. This is not part over whole times 100. All right. Moles of solute is 30 grams of glucose. I have to convert that to moles. How am I going to do that? How do I ever do a conversion? Grams in the bottom, moles in the top. 1 mole contains. Now, I didn't tell you glucose, but I'm going to save you trouble. Don't have to get a calculator out yet. Glucose is what? We all know it's what? C6H12O6, right? Right? I'm not going to make you add all those up. It happens to be right around 180 grams. What about kilograms of salt? How many kilograms of solvent do I have? I have 0.600 kilograms. I actually have 600 grams, which would be 0.6 kilograms, right? Now get your calculators out and do that. 30 divided by 180 divided by 0.6. What do I get?
There aren't any book problems on that.
No, I just had the matter of fact on my next slide. I just made them up this year. I have on about 5 problems that they are going to put on the back of the lab that we're going to do with this.
Okay.
So yeah, that's all I did for practice.
And did you give a quiz on this?
No, not on
Okay.
this. I gave. You probably have a copy of this somewhere in my thing. This is just a percent solution molarity. These are just percent solution ones.
Okay.
And then I have this lab. You did that one, right?
That one you gave me.
Yeah,
That's the one.
that's the one that has some molarity and molality and dilution ones in there, but none from freezing point. I just made them up, some for them to practice in the back.
I didn't know if you were sure.
No, just on the actually this year I just put them on here. So,
Okay.
and they're on my next slide. If you want to come over, you can get it
Well, I saw there's, I think it's like on the back of the
on the back of the
quiz.
quiz. Yeah, that's it. Well, this one sits in the back of the lab.
Okay.
There's the other ones that sit on the back of the quiz were for molality, because there are no molality questions there either.
No, there's none.
Yeah, so I just kind of made some up and put on the back of the quiz and back in the lab.
Okay. Yeah, I'll just find some more.
Yeah, you just yeah.
Alright.
All right. So what did you guys get? 0.278 molal. Now, don't think I'm done there. That's just the molality, right? What's my what do I have to do now with that? Delta TF equals KF times M. So it equals, what's my KF? 1.86 degrees Celsius per molal times 0.278 molal. I'm running out of room over here. So 1.86 degrees Celsius per molal times 0.278, the same number here, molal. Molal cancels, and it leaves me with what for delta TF?
5.17.
It shouldn't be 5.17. Maybe 0.517. Is that right? 0.517?
I did too.
Okay. So 0.517 degrees Celsius. Now, I didn't ask it in this problem. That is the answer for this problem. I did not ask it. But had I asked, what's the new freezing point, what's the answer? Negative 0.517, right? Because the old freezing point is 0, correct? So it'd be negative 0.517, right? All right, good enough. Now, let's just do a boiling point one real quickly. Boiling point elevation. As you know, if I add a solute to a solvent, as I've been telling you, it's going to raise the boiling point. As it lowers the freezing point, it's going to raise the boiling point. Not by the same factor, though. The Kb is a different number. What's some reasons I would want to raise the boiling point? I got a couple. You know, just like I don't want my car, I have to put antifreeze in my car so it doesn't freeze in the winter. What's another word for the same stuff you're adding to your radiator? Antifreeze or coolant. Yeah, it says right on the bottom, antifreeze/coolant. So you could use it for a coolant in cars, or you could use it for adding salt to water to make it boil at a higher temperature. How else can we make stuff boil at a higher temperature? We learned in the last chapter. Increase the pressure. Yeah, in a pressure cooker. Imagine if you had salt water in a pressure cooker. Wow.
Oh, yeah.
It'd be like boiling at 1,000,000,000 degrees.
Let's do it. So we have to throw it at the sun.
Yeah, it's like nuclear fusion. Same temperature as the sun. Get the stuff to boil.
I'm sure it's enough.
I don't think so. I'm just kidding. It would increase it though, even more. All right. So here's my equation. Notice the similarities. Delta TB equals KB times M. But again, KB is not the same as KF, and you don't have to memorize it. KB is 0.512 degrees Celsius per mole hour. That's 0.512 degrees Celsius per mole hour. Okay? I have two problems to do with this one for a reason. They're going to be, in one sense, easier and in another sense, harder, as you'll see. Okay, let me show you. Here's the first one. Now, if you read that one, you'll notice the sense that it's a little bit easier. In this case, I give you the mole solution. I don't have to take how many grams, convert it to moles, divide it by how many kilograms. It's already given to you. But I told you this guy's an ionizing solute, and that's a problem. Calcium chloride is an ionic compound that dissolves in water into ions. Okay? What is his formula? I got to know the formula for calcium chloride. Anybody know? Calcium has what charge? +2. Chloride? -1. Hey, here's a question right out of CaCl2, right? And that's my solid. Okay, here's a question right out of the test, right out of the worksheets, right out of what we're going to be doing very soon. What happens when I dissolve him in water? What happens to him? Do I get calcium plus chlorine gas, Cl2? Because a lot of people wanted to write that. No, I get calcium ions, aqueous, plus chloride ions, aqueous. And I have to include the fact that there are 2 chlorides. So there's 2 in front of that guy.
Why?
Why? Same reason I always do. I have to balance every equation.
Oh, never mind. I had my thing.
CaCl2 yields Ca plus 2 chloride ions. Okay. Now this guy, what does that tell me? What am I going to have to do to my answer here when I calculate the freezing point or the boiling point change? How many particles does this break up into? 3. So I'm going to have to multiply by the number of particles, 3 particles, whatever I get for my answer. So keep that in mind. But it is a very easy problem because the equation is just delta TB equals KB times M. And I already know KB and I already know M. So it equals KB, which is 0.512 degrees Celsius per mole, times the molality, which is 2.4 mole,
How do you know that? Oh, okay.
because it gives you a problem. So what do I do when I get that? Like 1.2, I guess, right? 1.2 degrees Celsius. But that's not my final answer. I'm going to phone a friend. Final answer?
Negative.
No, it is not negative. That's a really bad answer. I have to multiply him by 3 because it breaks up into 3 particles, which gives me 3.6, and it's still not my answer. And why is it not negative 3.6, Jared?
Because that would make sense.
Because that would make sense. What would make sense? What is the new boiling point? 103.6. You see the difference? In a boiling point, you're raising the boiling point, and the old boiling point for water was, everybody knows, is 100. Got it? All right, got one more problem to do. Just barely enough time to do it and then copy the questions down. The reason I'm doing this one is because I'm working it backwards. Take a look at that guy, working it backwards. I'm working it. Okay, determine the molality of a non-ionizing solute. This guy does not break up, so I don't have to worry about that. And I'm given the boiling point change of 1.32 degrees Celsius. Okay, can anybody figure out what to do on this problem? Should be pretty easy, shouldn't it? What are we going to do here? Well, let's write the equation down and see if it pops up at us. Delta TB equals KB times M. Right? Who am I trying to solve for this time? M. So what am I going to do to both sides? Divide by KB. And I get M equals delta TB over KB. OB/KB? Get it? OB/KB? Bill Cosby. Dentist. Okay. What's my delta TB? No, my delta is the change in the temperature.
Oh, 1.32.
So 1.32 degrees Celsius divided by the KB, which was still 0.512 degrees Celsius per molal. 3 Celsius cancels and leaves me with what for my molality? How much? 2.58. Everybody else get that? And that would be molal. Is that right? Look right for everybody? All right. This is easy. Manipulating a very simple equation. Okay? Whether it's delta TB equals KB times M or delta TF equals KF times M. Same basic equation. All right? All right. Copy these down. You have barely enough time on the back of your lab you're going to do tomorrow. This lab right here.